And when we started this work in about 1990, we had a dream that we might be able to create a millennial length absolute chronology. That's 1,000 years. We're now on the verge of 5,000. And I think with a lot of time and effort, we could get back to the end of the last ice age with these specimens, which would be sort of 12,000 years or so, maybe even a little bit longer, which would make these records comparable with the tree ring records we've got from Northern Europe and the rest of the Northern Hemisphere. And that opens up huge analytical capability.
Hello and welcome back to the State of the Earth podcast. Today we're joined by James Scourse, the head of the Department of Earth and Environmental Sciences and a professor of Earth Systems Science at the University of Exeter. With a research focus on how our oceans and climate have changed over time, his work brings together climate science, geology, marine ecosystems, and long-term environmental records to better understand how our planet responds to anthropogenic change. You're a very busy man, so thank you for taking the time to speak to me today.
It's fine.
So just to start off, you got your PhD in 1985, and since then you have held multiple positions and done a lot of work in the field of marine geology. When did you sort of first decide to go into the field? What sort of first drew you to it? You're a very busy man, so thank you for taking the time to speak to me today.
It's fine.
So just to start off, you got your PhD in 1985, and since then you have held multiple positions and done a lot of work in the field of marine geology. When did you sort of first decide to go into the field? What sort of first drew you to it?
Well, for my PhD in Cambridge, I was working on sort of the record of really ice age changes in the area around the Penryn campus, actually, West Cornwall and the Isles of Scilly and the offshore area. And it was largely terrestrial, what I was doing. It was terrestrial geology. I was looking at sediments in cliff sections, and I was looking at the fossil content, and I was dating the sediments, and I was working out a sequence of events, which was really delimiting and trying to work out the timing of ice advances to this part of the world. But I stepped offshore in order to put some more pieces of the jigsaw together, really. So I started off in the terrestrial realm, and then in the PhD I stepped offshore, and it was working with the British Geological Survey and some of the sediment cores that they'd got from this area. And on the back of that, I got a lectureship in marine geology. So it was really a kind of a fairly, well, it was just a small part really of my PhD, which was marine. But at the time, this is 1985, the oceanography, two of the oceanography departments in the UK were expanding quite rapidly, and there were jobs. And I applied for one, and I got one in Bangor in North Wales. And so I sort of converted into becoming a marine geoscientist through that experience. But there was a kind of resonance actually for me because, and I was attracted to working in the marine realm because I've got a long family history of people in my family being involved in seafaring in the sea and the Royal Navy, and my brother's a submariner, and and so the idea of combining my sort of passion for geoscience with the ocean was fueled by that sort of underlying interest, really, and background.
So for some people who might be listening who don't really know what marine geology really is sort of about, because it's quite I would say some people may have never heard of it. Could you give a little explanation about like what sort of fits under that umbrella?
Well, it's basically wet rocks. I mean, it's the seabed and everything that lies underneath it. And so you go right up to the coast, and there's obviously continuity because the rocks that you can find onshore extend offshore, and we know that, of course, through all the economic geology that takes place in the shallow marine environment in the North Sea, the hydrocarbons, oil and gas, and so on, and all the engineering work that has to take place in the shallow marine environment, cables, pipelines, and so on. And so we need to understand all the materials that underlie the seabed for stability, and you don't want pipelines rupturing and all that sort of thing. But when you go off into the deep ocean, essentially you have the oceanic plate being formed in the mid-ocean ridges, forming basalt, which are diverging or away from the mid-ocean ridges, and then like a sort of on a sort of moving conveyor belt in geological time, you have sediments accumulating on that conveyor belt. So you've got the oceanic basement, which is basalt, and on top of that you've got sediments, and those sediments are the ultimate repository for material in the Earth system. I mean, sediments accumulate in rivers, they accumulate in lakes, but ultimately those sediments are eroded and the materials are transported offshore. So the ultimate repository for sediments in the Earth system is in the ocean. And so it's the ocean that gives us the longest records of Earth's climate, Earth's environmental change. And those sediments stay there and are accessible to marine geoscientists until, in a geological timescale, of course, they get pushed down a subduction zone and they get turned into magma and then they're re-erupted in volcanic eruptions.
Yeah.
So all those things, all those different aspects, Earth's climate, plate tectonics, volcanicity, economic geology, all those things sort of combine in our study of what lies beneath the ocean waves.
It's a very interesting field. But yeah, you've done a lot of field work as well. You've been chief scientist of 12 different research cruises, I read. So do you have a memorable moment out in the field? Something that you thought was very good, or something you just remember fondly?
Many, yeah. Being at sea on scientific cruises is it plumbs both the depths and the heights. It can be ecstatic and it can be absolutely appalling. given the conditions, but yeah, scientifically, I think one quite recent really. I was PSO on the last cruise of the James Clark Ross research vessel. This is the ship that was replaced by boating at Boatface, or the Sir David Attenborough, in the Antarctic in just before COVID. So this was 2020. And I was there on 3 Antarctic cruises, and just going to the Antarctic was just absolutely amazing. It is quite an extraordinary place, and so that whole experience was amazing. But yeah, on the final cruise, we were in a place called Borgen Bay, which is a bay in Anvers Island on the West Antarctic Peninsula, and we were working close to the ice front, where the ice comes into the ocean, and part of the ice front collapsed while we were there, and it was captured on video. And we actually had a Sky News team on board at the time, and they captured it, and it went out on the news. Because these things happen all the time, of course, and they are happening all the time in Antarctica, but not always with a research vessel just there.
Yeah,
so
it's a bit of a tree in the forest situation.
Yeah, so it was opportunistic, and so the front started to collapse in one place, and then it sort of moved along, and so it was quite a big collapse in the end. And we initially had to move out of the field effectively fairly quickly, because we weren't quite sure what was going to happen, just from a safety perspective. But we then went back in, and we just decided to keep all the instruments running, because we recognised that we were in an unusual situation. We might capture some processes and capture some events which had never been captured before, because of simply the serendipity of having a research vessel right in front of an ice collapse. And through the work of BAS colleagues and physical oceanographers on board and geophysicists, we captured some events which hadn't been captured before, and were able to describe a completely new process in the way in which the physics of the water column responds to a big collapse like that, and how the water helps to get the water mixed up and heat move to the surface, and described a new sort of mechanism, for a sort of positive feedback mechanism for sort of warming up and helping the ice front to collapse even more. So that was it was interesting in its own right and sort of spectacular, but it was also demonstrates the sort of serendipitous nature of science. Often science, you can have the attributes of a scientist and you can sort of do all the right things, but ultimately some of it depends not so much on luck, but serendipity. some of the greatest scientists have just found themselves in the right place at the right time, and they've capitalized on that. And for other people, that doesn't happen, and it's not necessarily a reflection on them. It makes you realize that big scientific advances often are kind of quasi-accidental. That's part of the excitement, because you never know what you're going to find.
Yeah. You've done a lot of research, as you were mentioning, and in 2017 you moved your research group, Sclero, down here to Penryn campus. So what kind of made you choose to come down here to Cornwall?
Well, I think well, it was quite late in my career, so I hadn't kind of planned on a big move towards the end of my career. But as with all moves like that, I guess it's a mix of push and pull, and it's a mix of professional and personal. So and it was all of those things. It was push and pull, and it was professional, and it was personal. So but I just really love this campus. I think it's been great for me personally, and it's been great for my research group. And it's everywhere in the higher education sector at the moment is facing difficulty, but it's been a kind of exciting place to be, with lots of really good colleagues, and that was definitely a major part of the pull, along with the fact that from a research point of view, I mentioned that my PhD was sort of based down here. It sort of felt like coming back to a sort of early stamping ground in a way.
Yeah, coming back to Cambridge, your place. Yeah, so your research group is called Sclero, right? So you do research into long-lived bivalves and sort of look at their growth rings to reconstruct past environments, especially in the North Atlantic, right? So what is the process like for collecting the specimens? What kind of specimens are you looking for?
Right, I've literally just come from a seminar where one of my postdocs was talking about this. I mean, this started off really as a kind of sideline in my career. I was working mainly on sediments, and then through conversations with a marine biologist colleague in Bangor, I got interested in long-lived bivalves, and then we started treating them like a tree ring scientist treat tree rings, because shells have these increments in them which they're effectively little books about the history of the ocean in much finer detail than you can get from sediments, and that was attractive. And so what we're looking for are particular species that we know are very long-lived, and there's this one particular species, the Icelandic clam, Arctocara icelandica, which, as I've just been hearing in a seminar, and as we demonstrated actually in much reported in the press some years ago, can live to over 500 years. That's an individual animal living for 500 years, so you've got 500 increments within it. So that's a key species, but we do look at other species as well, which are also long-lived. But then some bivalves, like a scallop or a cockle on the seashore, will only live for 2 or 3 years, or maybe 5 or something. We need the ones that have quite a long record, quite a long lifespan. And so we go to situations where we know that the Icelandic clam is living, and as its name suggests, it's very abundant around Iceland. So the last cruise I went on in 2022, last big cruise, was to the North Icelandic shelf, and we were dredging for shells of that species there. We collected in just a couple of trawls, which were only about 60 meters long. We collected over 22,000 shells, which are proving absolutely fantastic for sort of developing our chronologies and developing our understanding of how the North Atlantic has changed over the last, now approaching several thousand years. The real advantage with looking at these is that you've got this annual time resolution. When you take a sediment core, it's not annually layered for a start. Exceptionally it can be, but almost invariably it isn't. And so you have to construct what we call an age depth model. You have to work out 1 meter down the sediment core, what's the age of that? Is it 1,000 years ago? Is it 10,000 years ago? Is it 100,000 years ago? And in order to do that, you have to apply various dating methods. And those dating methods have error bars on them. So you might get a radiocarbon date, and it might be 5,000 years plus or minus 40 or something. Whereas with a shell and the shell records, because we have replication as well, it has been described as an absolute chronology, in other words, without age error. But in practice, there are some complications. So it's probably, plus or minus 1 or 2 years. But basically, we've got detail in time to an individual year, and then within a year in some cases.
Right. Yeah. That makes sense. So, when you sample these, how far back can you tell? I mean, are you using strictly live samples, or is it just any shells, or does it differ between species? Like, have you tried to use other species that maybe, how far back can you reconstruct the environment using them?
Well, live collected material is really important because that anchors the chronology. So we know that the final increment is the present year. If you collect a dead shell from the seabed initially, you don't know when it started, when its larvae settled on the seabed, and when it died. So for live collected material, you're limited to the longevity of that individual specimen. And so, I mean, exceptionally, that could be over 500 years, but typically it would be less than that, maybe 200 or 300 or something like that. But because you have good years and bad years, just like you do with tree rings, you have variability from one year to the next. If you measure the increments very, very accurately, you build up what looks like a barcode of a product in the supermarket. You've got a sort of series of lines of different width. And for that specimen, that is the growth increment series for its life. And what we've discovered is that for other individuals that live over that same period, they encode that same barcode for the time when they're living together, when they were alive together. So what we do is we create these barcode records effectively, and then we statistically cross-match them so we can splice together, so we can get a live collected specimen, and we can get a dead collected specimen, and we can tell that for, say, 100 years, they were alive at the same point together because the barcode is the same. So we can splice those two records together, which means that then you can work out exactly when that dead shell died and when it started its life on the seabed. And you keep working back. And the talk I've just been to, actually, Tamara Trovimova, who's my postdoc, she's just been reporting on approaching a 5,000-year chronology for the North Icelandic Shelf. Hitherto, we've been limited to about 1,000 years, but through a lot of very detailed work, it's not quite there yet, but it's getting there. And when we started this work in about 1990, we had a dream that we might be able to create a millennial length absolute chronology. That's 1,000 years. We're now on the verge of 5,000, and I think with a lot of time and effort, we could get back to the end of the last ice age with these specimens, which would be sort of 12,000 years or so, maybe even a little bit longer, which would make these records comparable with the tree ring records we've got from Northern Europe and the rest of the Northern Hemisphere. And that opens up huge analytical capability, because it means we can compare what was going on in atmospheric climate recorded in the tree rings with the ocean climate recorded in the shells.
So, sort of on the coattails of that, does this, like the specimens you measure obviously from the North Atlantic, could this sort of method be applied to other areas in the oceans? Is that needed? Do we have, if we have a North Atlantic sample, like, does that kind of give us a good enough understanding? Or, could you apply basically the same method to other places?
You can definitely apply the same method to other places. The records we're getting from the North Atlantic are telling us mostly about what's happening in the North Atlantic. Sometimes it's giving us more regional information than that. It seems that some of the volcanic eruptions from Iceland might be recorded in the shells, so that's quite a local impact in that case. Exceptionally, you would be able to detect things in the records which have significance at a global scale, but really you need to develop chronologies in different places, records from different places, to tell you what's happening in different places. And that was the primary reason that I got involved in working in the Antarctic, actually, because I was approached by some Antarctic scientists speculating on whether there were equivalent very long-lived species of bivalve living in the Antarctic, which we could treat in the same way to create long environmental records from the Antarctic. And there are all sorts of very good scientific reasons why that would be a good thing to do. And so, and almost anecdotally, if you read the sort of marine ecology texts, it sort of states that the polar oceans in particular, the seas around Antarctica, the water's incredibly cold, and the animals, the organisms live for extremely long time and all this stuff, low metabolic rate. And so we had high hopes that we'd be able to find something that would be as equivalently long-lived. Our hopes were sort of dashed, though, really, because we haven't found, we found some species. Equioldia eitzii is the name of it. It changed its name from Yoldia eitzii fairly recently, but it's just the size of a thumbnail, and it has a record of maybe 50 or 60 years. And we can cross-date, we can cross-match it and cross-date it, but so far the records we've got there are just a few decades. And so hitherto, so far, we've not found anything that is as exciting as Arctica Icelandica in the Antarctic, sadly.
Yeah. So it's sort of only kind of, bivalves is like what we know and how we already have data on it, so we know how they absorb all these things, how they create them. But is there any sort of like, for example, in warmer seas, like maybe fossils of like coral reefs? Would that be sort of, do you think it's viable? Do you think that makes sense?
Absolutely. I mean, the coral community is a sort of sister community to us, and all the conferences. We're about to go off to AGU in Glasgow week after next, and that's the Ocean Science meeting, and there'll be lots of coral people there, and folk who work on the subtropics and the tropics, and coral communities have the coral produces annually resolved records, so that you can get some idea in a very similar way of changes in the climate and the ocean climate in those regions. For instance, the El Nino type sort of cyclicity is present in the coral records from the West Pacific. So that's possible. The constraint with coral is that, unlike the shells, you're limited to one. You take a core through the coral mound. It doesn't kill the coral, but it just takes a very narrow core, and that's what you study. But you've just got one core. It's a bit like a sediment core. And so you can't really do cross-matching or cross-dating because you haven't got lots of specimens to match together. So you're interrogating something. You're limited to the longevity or the length of that record in the coral. But the science is very similar, apart from the cross-matching, cross-dating side of it. The kind of geochemistry that you'd look at, stable isotopes and trace elements and so on, would be very similar to the kinds of things that you can do on bivalve series.
Yeah, and definitely now that coral reefs are really struggling, you have to find a specimen or a species that is alive, and there is a high population number, I guess.
You can of course do the same thing and the equivalent in a bivalve would be what we call a floating chronology, and you can construct a cross-matched series of all these dead shells that match together and create something that's quite long. You can pin it at the end with radiocarbon ages, so you know approximately when it was. That's quite useful. And in the same way, you can, and this has been done in ancient coral reefs in New Guinea and the Caribbean and so on. You've got fossil coral in fossil reefs, and you can take cores through those, and you know that from, for instance, uranium series dating, that reef is 120,000 years old, and you can take your core through the corals, and so you can get an annually resolved record for a chunk of time that you know was approximately 120,000 years ago. And that's useful because that's giving you some idea of, interannual variability, some relatively high frequency cyclicity in the climate system through a particular phase of Earth's climate. And so just because it's not cross-dated, or or even cross-matched, an annually resolved record from something that you've approximately dated can still be very useful.
Yeah, and definitely now that coral reefs are really struggling, you have to find a specimen or a species that is alive, and there is a high population number again.
We already are.
Yeah, okay.
Yeah, so I mean, two sort of things. My colleague Dave Reynolds, who's in the department here, he sort of pioneered taking these shell records, shell series from all the way around the North Atlantic and sort of creating networks so that you can build a picture of what's happening right across the North Atlantic, looking at the common signal between these different records, and that's proving really, really valuable for the climate modelers, because one of the issues with climate models is that you can compare the climate model simulation output with the instrumental measurements, but the instrumental measurements don't go back very far. And the instrumental measurements, more to the point, they are covering a period after which the human impact on the environment has been profound. So your instrumental measurements are not measuring, if you like, baseline conditions. They're already measuring disturbed, profoundly disturbed bit of the climate system. So for climate modelers, it's really valuable to have what we call baseline records, which record, for instance, the period before the Industrial Revolution, before global warming really kicked off. So you can see the behavior of the ocean system or the ocean atmosphere system before it's been perturbed. And those long series are immensely valuable. So that's one application. Another thing we're doing is with Paul Halloran's group, Paul Halloran's colleague in the Streatham campus. We work with him quite a lot, and he's done some amazing analyses where we take the tree ring record, which is a record of atmospheric climate change, and you can compare that with the record from the shells from the ocean, and you can see the phasing between what's happening in the climate of the atmosphere compared to the ocean, what's leading what's lagging behind, and that's been really revealing. And again, Paul's group with his research student Beatrice Arellano Nava has started to look at the behavior of the growth increments leading up to major climate changes. For instance, the shift from the period of relative warmth in the medieval into the Little Ice Age in the sort of 1300s, and looking for signs of a tipping point within the Earth's climate system, or within the ocean system in that case, and looking at statistical indices like autocorrelation and variance, and signs of lack of self-regulation, which would be a sign of a system about to sort of flip into the new state. So the answer is yes.
So you mentioned before, just briefly, like the atmosphere, obviously marine world and the atmosphere, they feed into each other. Do you think it's that things that happen in the atmosphere then have effects on marine, or is it like a feedback?
It's a complex feedback, yeah, and in all sorts of respects, it's a complex feedback in terms of heat and in terms of, for instance, CO2 flux. So that if there's more CO2 in the bottom of the atmosphere compared to the surface of the ocean, there'll be a flux of CO2 in, and then if it's the other way around, there'll be a flux of CO2 out. So the coupling between the ocean and the atmosphere is incredibly complex but important, and you have all these feedbacks. But just an example that I just talked to you about in terms of phasing. Analysis of the last 1,000 years would suggest that the ocean until 1850, in other words, until the major phase of global warming kicking off, changes in the ocean appear to lead changes in the atmosphere. So you get a change in the ocean currents, you get a change in the ocean heat supply, that feeds into the atmosphere. But then post 1850, that reversed. And so the intense warming of the atmosphere as a result of the greenhouse effect, as a result of fossil fuel burning, was actually then driving changes in the temperature of the ocean. So that phasing across that critical boundary has been quite revealing.
So does it sort of because it's flipped around, does it sort of amplify the effects of climate change, in the ocean? If it used to do one thing, now it's doing the complete opposite because it's being affected instead of affecting.
I think it's difficult to say just from that whether it's amplifying it, whether that change of pattern. Of course, we don't know in the natural system yet whether that phasing is flipped in the past, but certainly for the last millennium, it's quite distinctive, and quite what the ultimate impact on the amplification of global warming is, I think, is probably an open question.
Right. Yeah, so you've also mentioned a little bit about your work on glaciers. You do a lot of also you do stuff on land, how glaciers retreat, how they affect the landscape. How is this kind of research done? Is it sort of more field work based? Do you use sort of satellites? Like, how do you see these? Because these are quite sort of, I guess, big scale changes. How is this kind of work done?
Yeah, I mean, it's fairly classical geology. There's a lot of field work involved in looking at, on land, glacial landforms, and then the sediments that are associated with those landforms, dating those sediments and so on. But I would say that it's been transformed over the period of my career, not necessarily through any work that I've done, but through work colleagues have done, because two things have happened really. I remember going to a meeting in about 2006 or so at St Andrews of a professional organisation that I belonged to. And suddenly it's one of those moments, it was sort of annual meeting, and normally people just sort of updates on what they've done previous year and all this kind of thing. Suddenly there was boom, it was mind blowing, because two things had sort of suddenly arrived. One was sort of digital terrain mapping and LiDAR on land, and so areas we thought we knew from field work was suddenly revealed to have a whole structure of landforms and elements in the landscape that had never been detected before. So you've got these incredibly detailed representations of the topography of the land surface, and that's revealing, for instance, mega scale glacial lineations, flutes, drumlins, moraines and things which hadn't really been pieced together at a landscape scale before. In parallel with that, you had the development in the marine realm of something called multi-beam swath bathymetry, which is effectively where energy is put into the ocean sort of obliquely on the side of a ship, and you've got whole streams of geophones behind, and they collect the data and they basically produce the same but maps of the seabed. So suddenly we had all these maps, both of the land, incredibly improved, or images which are incredibly improved, and of course the terrestrial images are supported by satellite imagery as well. So you've got that imagery of the land in conjunction with the imagery from the ocean bed, and you put those two together and you can begin to see patterns which relate to the former flow of ice sheets, the margins of ice sheets, the direction in which they were flowing, and so on. And so what that does is it then guides you for field work, because instead of just sort of going out with a hammer into an area that you think might be vaguely relevant and sort of finding an exposure that appears to have something that might tell you something, it can direct you to a particular place, and you can sort of go, and it's more structured. It's more, the imagery is generating hypotheses for field testing. So you can go out there, whether it's with a ship offshore to take a core, or whether it's on land to go to an exposure, and then you can have a more structured field campaign, collecting samples for dating, taking samples to determine the nature of the sediments in terms of the glacial environment. And so that's been transformative. And so that's really the way it's done now. It's sort of, it's a conjunction of imagery with field work, and then really detailed and analytical work to date things.
Okay, yeah, that makes a lot of sense, and that's good. It's improved the way that the science is done, so it can only be a good thing. So now that you've mentioned a bit about glaciers, people are very worried, obviously, about how the glaciers are looking, how they're retreating. So do you think, based on your own experience studying them and working, obviously they're retreating. Do you think if climate change were to ever be reversed, how would they reform? Would it be the same level? Would it take a long time?
Well, if we didn't have anthropogenic global warming, if we hadn't had the Industrial Revolution, if we didn't have ongoing fossil fuel burning, even though there's been some positive news about that today, which is very heartening. But if that had not happened, we know that the Earth has started its slippery slope to the next ice age. The Earth has been kind of pulled out of that natural trajectory and completely pushed in completely the opposite direction. It's completely overprinted that slow cooling trend. But we know this because what's driven a whole series of ice ages through the last few, certainly the last few millions of years, has been the position of the Earth in relation to the Sun. These are the Milankovitch periodicities, and amplified by the natural carbon cycle on Earth. And these cycles are entirely predictable. They're as predictable as the tides. You go down to Falmouth at 5 o'clock. What's the tide going to be at Falmouth tomorrow night at 5 o'clock? Well, we in the department, we have the annual sandcastle event, which depends on the tide, when we have all the new students in the first year coming in building sandcastles, and I need to know what the tide's doing. And so I look at the tidal prediction, probably several months in advance, so we can sort out what's happening in Welcome Week, and I can look at the tide table, and that is a prediction of what the tide's going to be on that particular day. And so we can schedule that event according to that tidal prediction. Well, over much longer timescales, ice ages are as predictable as the tide. A span has been thrown in the work because of anthropogenic global warming. But if that wasn't the case, we would probably, in several tens of thousands of years, be experiencing a full ice age again, the next ice age cycle, because there's nothing we can do, fortunately, to change the Earth's orbit around the Sun. These are natural. They're actually driven by primarily the gravitational relationships between the bodies in the solar system, and we can't impact that. So we would go into the next ice age. And what would happen? Well, we can see from previous ice age cycles that you can go from relative warmth, like we've experienced for the last 10,000 years, which we call an interglacial, and then it's a relatively slow process to build up the ice. It takes a long time. It depends primarily in any particular region on kind of counterintuitively rather cool summers, because if you get snow will fall pretty much in the mid and high latitudes every winter, but if it doesn't melt in the summer, it starts to build up and eventually it turns into ice, and so it starts in the mountain areas and gradually get valley glaciers, and then you get ice caps, and then they coalesce, and hey presto, you end up with a big ice sheet. That process takes thousands of years. So ice takes a long time to build up. Conversely, it can be quite rapid to get rid of ice, because once the ice starts to melt, and that melt gets into the ocean, sea level starts to rise. That sea level rise affects the margins of the ice sheets that are sitting in the ocean. The ice then calves off very fast, and you get a process called downdraw, and the whole thing just collapses very quickly. And that's what they're worried about in West Antarctica at the moment, because we're seeing sea level rise. So sea level rise at the margins of the ice sheets is an incredibly important kind of relationship in driving deglaciation. And so it's asymmetric. So the build-up of an ice age, if you like, is very slow, but then the end of it, the deglaciation, can be incredibly rapid. And I mean, records from the ice cores would suggest that the end of the last ice age probably was accomplished within one human lifetime, whereas the build-up is tens of thousands of years.
Wow, so that that makes me a bit more scared about the tipping point of it.
Yeah.
So
So deglaciation is very much more rapid than glaciation.
okay, that makes a lot of sense. Yeah. So you also mentioned before you do a lot of like seafloor work with the core samples and stuff. Have you ever been approached for having that sort of data or sort of your expertise to be used in like mining or all these sort of more economic or
I do have strong personal views about deep sea mining, and with colleagues, we wrote a paper recently, my colleagues in CSM, about why we shouldn't do deep sea mining, which was, I think, important to do. It was stimulated by me hearing a story on Radio 4 as I was eating my breakfast one morning. They had some people from mining companies saying that they were going to go off and put a combine harvester across the deep ocean, and I just thought, oh heavens, And so I convened a little group of a range of expertise in the department, and we put our heads together, including mining engineers, and then we wrote this paper which got into one of the Nature journals, and about most of the papers have been on the ecological impacts, which would be pretty desperate, or the oceanographic impacts, but this was a slightly new angle because it was, and I hadn't realised this until we actually convened this group, that frankly there's nothing in the deep ocean that we can't access much more sustainably from on land. So there's no need to go there in the first place. The whole thing's being driven by big engineering companies that have tech that can go underwater, and they're trying to find a new use for it.
right.
So that the whole deep sea mining thing is being driven by technology and companies rather than some sort of need.
And I guess lack of regulation maybe in the ocean, it's a whole new thing, so you don't have to have the same permits or
Sort of Wild West.
yeah. So it's first gets there first.
Yeah, but coming back to your first question, it's interesting actually, because I've done a lot of work on, going right back to my PhD on the Celtic Sea, and this has all been academic work, and it's been looking at the sort of the sediment record and what's on the seabed and the landforms on the seabed, etc. And this is all mainly in relation to glacial history and that stuff that we were talking about earlier. But these days, when you have things like ResearchGate and so on, and you can see how many people are reading your papers, and you can see how many people are citing your papers, and so on. And I suddenly noticed that in some of these papers we'd written about the Celtic Sea, starting about 5 years ago, there are huge numbers of reads and downloads, but disappointingly rather few citations. But there was a definite trend in a certain group of my papers. And then in conversations with folk who are working in floating offshore wind and the consultancies who are engaged with renewables offshore, it became clear that you had all these consultancies and groups who were actually researching ground conditions for anchoring floating offshore wind turbines, and they were just collating all the information they could about the nature of the sediments on the seabed and underneath the seabed. So and this is always happening in science, and why this blue skies research should never ever be devalued or not funded, because hey presto, if we hadn't done that work, which was purely academic, then that body of data wouldn't be there for a sort of economic use in terms of renewable energy. So I'm very happy people are reading my papers. I just wish they'd cite them a little bit more.
More research in your field would be it'd be good. It's needed. So I mean, when I was reading up on you, I was fascinated to see all the positions you'd held. For example, you were president of the Quaternary Research Association from 2008 to 2011, and you were also part of the NERC, part of the Radiocarbon Facility Steering Committee, and all of those sort of positions. What is it like to be in these roles, how do you manage them alongside your research? Was it sort of a job on top of a job, or were you able to advise from your role as a researcher?
Yeah, I mean, they are, you carry on with your day job and carve out a bit of time to do these other things as well. And I think, now I'm head of a department and always encourage staff to take on these roles because they're very beneficial for professional development. They give exposure to members of staff, to the wider network, the wider community, but they're also immensely valuable because you learn such a lot by sitting in panels reviewing. And, in the Radiocarbon facility, I was with a whole panel, but reviewing proposals on things I knew nothing about really. And I wasn't necessarily reviewing the ones I knew nothing about, but listening to other colleagues who did know about them and getting their perspectives. So you've got a proposal in front of you, you read it, and you think, oh, that sounds really good. I think that's the, and then an expert from some other university will start picking holes in it and say why it's perhaps not as good as you thought it was, and you think, oh well, yeah, okay. So in that process, you build up a huge sort of bank of knowledge about different aspects of the science that you do, different areas, different applications, and so on. I'm sitting now on something called the Science Commission of Flanders, which is basically in Belgium, has two sort of research councils split down the middle of the country, and I'm on the Flanders bit, and it's involved in sort of major infrastructural funding, millions and millions of euros being funding certain bits of science infrastructure, and these now go way beyond my expertise. Most of them, it can be medical science or it can be big telescopes or whatever. But it's fascinating because you're learning all the time. And then another time I was on for quite a few years, I was on what's called the University Research Fellowship panel for basically physical sciences for the Royal Society, and Earth. So I was representing Earth science, and that was fine. But I was also having to sit there in a panel with astrophysics, particle physics, and condensed matter. So there were applications about CERN, about particle physics, about the Higgs boson, and then about black holes and dark matter and so on. So it's way outside but it's just fascinating. Yeah. So you learn a lot by doing these things.
Yeah, definitely. I guess in a way it grows so that your research can then also link to other disciplines and other things which you might not have realized, I guess, were
exactly
linked.
Exactly.
Yeah.
Yeah.
So you were also the director of the Climate Change Consortium of Wales. How much of that role was sort of advising on policy, or did you get to have?
It was pretty good actually. It's a bit of a slow start, but by the sort of last 2 years, we were reasonably regularly contacted by the Welsh Assembly, Welsh Government in Cardiff, and the AMs from the equivalent of MPs sitting in the Senedd in Cardiff, and able to feed in a much more direct way actually than ever happens in England. I don't know what it is. England seems to have much more tenuous links between science on the ground and policy. It's much hard, in my experience. The reporting route is not the right word, but the sort of complexity of the channels between those who are making the policy and those who are actually engaged on the ground doing science is much more distant. In Wales, there was a much closer interface, and the civil servants and the AMs and the ministers, they kind of knew us by name.
Yeah, and I guess it sort of does show you that maybe we need more scientists to be taking part of the policy aspect of it, to get involved in that. If there was more positions in government.
Exactly, I completely agree. And some years ago, I took part in a public debate with a climate skeptic MP in the borderlands of Wales. And there was a big public meeting. It was part of the Climate Change Consortium for Wales job, really. And it was clear that he had absolutely no scientific understanding of even the most basic elements of climate science in the discussion and in the debate. And I commented we had to make closing comments, and my closing comment was, I thought it was pretty desperate that there weren't far more MPs who had some scientific training. The vast majority have no or very little scientific background. And shall we say, he took me to task after that because he thought it was below the belt, but I thought it was a fair comment. You can still find it on YouTube if you really want to.
Yeah, I might do that. I just see that. So sort of as a wrapping up question, is there any unanswered questions in your field? Anything that if you want to take your field somewhere in the future, if there's any new research being done that you think like that would be the next step of, climate science or marine geology, or anything that you think you'd like to see the outputs of that research, maybe your own?
Where do you start? There are so many, and the seminar I've just come back out of is really exciting, and sort of, I'm sort of not far off retiring really, and I thought I've got 2 big projects running, and they're going to run for another year or so, and I thought they'd probably see me out, but I've got really, really keen about putting another proposal in, so I might do that. And yeah, there's an application of these shell records that I've got really interested in following up, which I think only our group is in a position to do, because we're the only group that have the records of the longevity that you would be able to apply this to. Yeah, I don't want to say too much more, but it's because it's just at the point where I'm probably going to start writing, but it's I don't really want to stop, to be honest.
No, and I guess when you like something that you do, it's a vocation. There's no reason to.
Yeah, no, I'm definitely not gonna. Even when I retire, I don't think I'm just gonna hang up my boots and go and drink coffee. I can't imagine. I might watch a bit more cricket, but hey, that would be nice.
The science world would miss you. So thank you so much for joining me today and speaking to me. And to all of our listeners, thank you for tuning in today, and we'll see you on the next episode of the State of the Earth podcast.